Well, so we'd like to starting off the second portion of this session. So we have, let's say, a guest from that. We have the guest of the Professor Michael Short from that MIT. But before that, let me introduce that the Mr. Professor Michael Short. So that the prof, the first joined the MIT's Department of the Nuclear Science and the engineering that as an undergraduate schools in 2001. And then after graduate school, the postdoc, the research scientist position, he joined the faculty in 2013. So he specializes in experimental nuclear materials, alloys for the advanced efficient fusion, measuring radiation damage for nuclear security and enhancing nuclear and graduate education. Professor Michael Short, the floor is yours.
Thank you very much, everyone, for coming. こんにちは、皆さん。ショートマイクロと申します。どうぞよろしくお願いいたします。ちょっと自分の日本語でご紹介。
So that, let me just introduce myself in Japanese.
ちょっと通訳を聞こえません。大丈夫ですよ。まあ、実はMIT も生まれも育ちも MIT ですね。実はボストンで生まれて、小学校の時からよく MIT 行きましたよ。博物館に行くやセミナーなど。じゃあ、そうして大学生も大学院生、ポストドクも研究員、そしてやっぱり先生になりました。じゃあ、ちょっと今はボストンには夜中なんですから英語で話を出してあげます。じゃあ、通訳者さんにお世話になります。そうして私の話が早すぎる場合は減速するようにどうぞ頼んでください。じゃあ、それから英語で話します。If that's okay with everybody else, I'll continue in English. So I'd like to present to you what's a little bit different about education in the US, maybe compared to the way it is in some other places, and what I believe MIT makes very special. I've worked quite hard on some of the upgrades to the educational curriculum here, and I'd like to echo Professor Obara's invitation for everyone to come to MIT, whether it's for a conference, or for academic exchange, or to apply to graduate school. If you do, and you want a, I'd say, Japanese-friendly introduction to MIT culture, I can do my best. So, as we all know, the nexus of nuclear power is shifting to Asia. It used to be that the US was the main center of nuclear power, and now it becomes Japan, South Korea, China, India, and other places in Asia. And we believe that nuclear power is absolutely necessary to combat climate change. That's why I study what I do, is because I'm an environmentalist. But there's a question, is the world doing what it must? I would argue no, because all over Europe, nuclear power is not popular with the general public. And if you look in the US, a similar situation is happening. By the year 2050, the US will have zero nuclear power if we don't change something. The cause is exactly what Professor Obara mentioned. We need to attract more talent. That's you. We're looking specifically to attract smart and interested students to join the nuclear field. The issue has been that until recently, nuclear education looked something like this. And when I would look out in the audience, the average student looks something like this. So it's our job to very quickly evolve US nuclear education out of the 1960s in order to attract talent and solve the biggest problem facing humanity, which is climate change. So nuclear at MIT is different from elsewhere. There's a few words that I like to use to describe what makes nuclear graduate and undergraduate education at MIT unique. Starting off with learning objectives, the next thing we do is try to make it personal. This isn't just some field of theoretical physics. We try very hard to make everything we do personal. I'll explain how. We try to make it innovative, like Adrien Couet was just describing, and experiential or experimental. Even the most dry and boring courses can be highly experiential. And when you get to experience nuclear science and engineering, it suddenly becomes more fun. By the way, this PIE stands for post-irradiation examination. I always like how that works out. We focus on design of open-ended problems because the problems that nuclear can solve are not simple math and physics equations. They're major societal challenges that require social constraints in order to design workable solutions. And I'll show you an example of what our students created this year. We always focus on assessment by some unusual forms. We focus heavily on communication with other students, with members of the scientific community, and especially with the general public. And we build community. The people that are in nuclear really believe in it. And as you could tell from Adrien Couet's presentation, the people here really stick together because we believe what we do is important for the world. And above all, it's what I call transdisciplinary. I'll explain what this word means because until a couple of years ago, I had not heard of it. So transdisciplinary education is not about disciplines, it's about issues facing society. Rather than say, I'm going to study nuclear engineering, you lead with the idea that I'm going to stop climate change. I'm going to save the world. How am I going to do that? By studying the only one subject that really exists, life in all of its manifestations, one of which we've made available as nuclear power. And the way we view transdisciplinary education is it's not just awareness of other disciplines. It's not just sharing or correlating things. It's not even interdisciplinary. It's what we call transdisciplinary, where the focus of the education is about the problems and the solutions, not about the theory and the disciplines. You learn all the same things, but for a more important reason. And so there's a few quotes I'd like to leave you with. In the field of nuclear, I like to say we should be more encouraging of responsible insanity. It means, anzen demo, chotto crazy na koto ga ii desu yo. So I want to show you some examples of experiential learning that you can get while at MIT. Let's say I asked our students to calculate the radioactivity of a banana. Some of us know that our food is all radioactive. It contains naturally occurring radioactive isotopes. You can either approach it theory first and go right to the blackboard. Honestly, this is kind of boring. Or you can do what we did and have our students figure it out by experiment. So we asked our students to each take home 25 kilograms of bananas. I bought 500 kilos of bananas from the grocery store, gave 25 kilos to each student, asked them to peel them and burn them in the ovens in the dormitory. The whole campus of MIT smelled like banana bread, and only the nuclear engineers knew why. And we took the ashes of these bananas, put them in a gamma spectrometer, and measured the width of the potassium-40 peak to measure the radioactivity of the banana. Then this allows students to latch theory onto real experiences. Because nuclear things, in the end, they're real. They're not theoretical. Everything has a basis in reality. So we create that reality in the classroom and in the laboratory to help you remember what makes this field so interesting and so crazy. This year, we actually looked at the radioactivity of gummy worms and wasabi peas by request of the students. It turns out wasabi peas were more radioactive than bananas, while gummy worms had absolutely no radioactivity. probably because they're made only of sugar or corn syrup, and they have no nutrition and no nutrients. Another example, let's take the case of neutron physics. You could approach this from a theory-heavy class, or you can do what one of our undergraduates did and build a 3-meter cube of graphite with 2 tons of uranium metal rods that we've rebuilt in the last few years. And our students load this reactor with 2,000 kilograms of uranium metal and measure the criticality as they add uranium. Then they compare with their calculations and numerical simulations to understand the physics of why criticality goes down when you add more fuel, depending on the geometry of the reactor. These can be very difficult to understand only from math, but when you actually get your hands dirty, I mean, look how dirty our coats get, right? When you get really filthy, then you really start to understand the intuition, the physics, and the science behind what you're doing. We also like to draw in students with emotional connections by making the material personal. And this is something I can promise you. If you come to MIT, I will ask for your toenail clippings, and we'll put them in the MIT nuclear reactor to perform nuclear activation analysis and study the amount of different heavy metals in your bloodstream. For example, we measured arsenic, chromium, scandium, and gold. The gold was an interesting one. I asked the students to please remove the toenail polish before they gave me their samples. And in one student, I measured very high concentration of gold. And I asked her, did you remove the polish? And she said, yes, but I live in South Dakota state. And in South Dakota, there's a lot of mining activity for gold. So it turns out we have an expression in English, you are what you eat. Well, using this personal lab activity, we can measure how much you are what you eat to a precision of about 10,000 atoms. And so when you come to MIT, I'd be happy to irradiate your toenails. We teach the process and the method. The answer is not as important as the way of thinking. The problems that we'll give you emphasize open-endedness and flexibility. In fact, sometimes we give you the answer. The problem statement might be very small. For example, estimate the additional dose incurred by spooning. If you don't know what spooning is, I have a diagram here to show you. If you sleep next to someone for 8 hours, you get a dose of about 0.01 microsieverts. And we teach the process of how to model this system. Let's say as 2 dogs, one self-shielding from the other, and perform a ray tracing integral to calculate the dose that one dog irradiates the other. So again, this isn't so much about the answer as it's about the ways of thinking. This is how we teach nuclear innovation, is it's a different way of thinking. We also want to provide lots of real-world examples of this discipline in action. So something I asked my students to do, I'll play this video, was remove the sources from smoke detectors, which all contain americium-241. 少し少しだけ違法されていますが、大丈夫ですよ。英語で通訳してしたくないんです。And in the end, you can actually see the blue light emanating from alpha particles. Each one of these circles is 600 alpha particles worth of radiation, causing scintillation and blue light. You can see this with naked eye in a dark room, in a very dark room. And that way you can actually visualize with your own eyes the amount of radioactivity in a certain source. We also focus heavily on design throughout our curriculum. In many old nuclear engineering curriculum, there would be maybe one design course at the end of the 4 years. Maybe even graduate school would have no design course. At MIT, you'll have one every year. The first year, the first thing you do when you arrive on campus is we ask you to build, test, and use a Geiger counter. Even this year, during the COVID pandemic, I sent each of our students this Geiger counter kit. I sent them soldering irons and safety glasses, ansen wa daiichi, ne? And I asked them to build this Geiger counter and walk around their town to find the most radioactive places they could find. And I'd be interested in the Q&A. Please tell me, what radioactive places do you think you could find near your homes in Tokyo? I can think of quite a few. In the second year, we teach a course on design thinking. There's not necessarily anything nuclear in this class, but we want to teach you how to think from a designer's point of view. In the first week, we'll ask you to make something from the worst possible material. These students made a cleaning mop out of frozen yogurt. It still has to work. It still has to meet functional requirements of a design. But you also have to explain what makes it a bad choice of material, because then you can explain what makes it a good material. Using these design thinking skills, the prototyping skills from the first year, and the theoretical knowledge throughout the course, we get into nuclear design in the fourth year. And I like to say nuclear design should not end up in a desk. It should change the world, and it should matter. In 2017, for example, our undergraduates discovered that by exposing plastic waste to gamma radiation and mixing it with cement paste, they can produce concrete 15% stronger than ordinary cement. After this design course, this led to 2 scientific papers, 2 patents, and a startup company, Micon Technology, which is still active today. So we founded a company directly based out of our design course. This year, I asked our students to take on an anthropologically informed, culturally acceptable way to decarbonize Ulaanbaatar, Mongolia, the capital of Mongolia. We did this despite COVID restrictions. So you can see the students are still spread out and all wearing masks. At MIT, we don't have so much problem with people not wearing masks like in the rest of the US. Massachusetts is a very science-focused state, and so you can be comfortable that things are a little more sane here. So to introduce you to this problem, Ulaanbaatar is the world's coldest, most polluted capital city. And the most vulnerable people live in these gers, nomadic tents. Then they're dependent on the government for their livelihood. And in the summertime, things look okay. But because everybody burns coal in their houses and thermal power plant, this becomes Ulaanbaatar in the wintertime. The levels of pollution are so high that respiratory disease is the leading cause of death this year in Mongolia. And at the heart of every home is a traditional Mongolian stove, which provides the heat and the heat for cooking. This is the heart of the household. Asking people to change their lives and throw out these stoves is not possible. And so what the government did is they banned the use of coal and instead asked people to burn charcoal briquettes. But without knowledge of how to burn these properly, they produced carbon monoxide. Thousands of people got sick from carbon monoxide poisoning last year. And this year, the first night of winter, 40 people died from using this fuel. This is an example that doesn't work. These are the sorts of inappropriate systems that we teach you in the nuclear department to think around. There's a team from a different university that said, why not just add insulation to the houses and use an electric heater? Well, the cost of the solution was $400, and the median annual income of a family is $1,100. This is much too expensive for people to afford. In addition, using electric heaters makes the pollution problem 3 times worse. Can someone tell me, Q&A to chat de kotaete kudasai, why would using electric heaters make the pollution problem so much worse? Dareka kotaete kurete mo ii desu ka? ちょっと恥ずかしくてもういいですよ. I'll tell you a little bit later. So our students analyzed the amount of energy required from each Mongolian household based on the amount of coal that they burned, and figured that by adding some cheaper insulation to the outside of the ger, they could reduce the energy requirements from 500,000 kilojoules to 93,000 kilojoules per day. The rest can be made with a molten salt heat bank, a zero carbon thermal energy storage system, which our students prototyped. They built a model ger using the same felt material as you would find in the ger, a scale model, equipped it with temperature sensors and remote controllers, added different types of insulation, prototyped a molten salt heat box, heated it to 400 degrees Celsius, and using thermal imaging cameras, tested how long it took in order to keep the ger warm, estimated the cost of the solution, and calculated the payback period, and finally designed a molten salt reactor that could provide the heat required to heat enough molten salt bricks for every ger in Ulaanbaatar, making a solution that's 20 times cheaper and doesn't make pollution worse. By the way, the reason electric heaters make pollution worse is because the electricity has to come from somewhere. It comes from the thermal power plants, the coal burning power plant. And it takes 3,000 megawatts of coal to make 1,000 megawatts of electricity due to thermodynamic efficiency. And I should also mention, 5 years ago, our design course developed the arc fusion reactor, spun out Commonwealth fusion systems, which to date has raised over $250 million in 5 years to build a fusion power plant to create net fusion energy before ITER. So if you want to be a part of fusion power in the next 10 to 15 years, please come to MIT. MIT research is leading the way in making this reactor a reality. Our fission thermodynamics folks are designing molten salt breeding blankets. Fission materials people like me are picking the structural materials for the fusion reactor. We have plasma physicists, diagnostic folks, cryogenics engineers, artificial intelligence experts, mechanical engineers, civil and environmental engineers for balance of plant, policy and anthropology folks to deal with public acceptance and regulation. We need everyone, not just nuclear engineers, to make this a reality. We have the money, we have the goal, we have the vision. All we need is you. And the last thing I'll mention that we drill specifically is communication, not just through writing papers and other things. So the last thing that we drill is communication. This is not just through adding communication assignments to classes. We also have a communication laboratory we call the Communication Lab. It's peer-driven, collaborative learning. We focus on students training other students to communicate effectively in science and to the general public. We create a supportive, positive environment so everyone can learn how best to give seminars within your discipline or targeting different types of audience like undergraduate populations, general public, ways that you can talk to your family about the science you do. And we provide just-in-time delivery, meaning if you have a talk to give in the next 3 days, we can still help you. And we actually assess this by data-driven assessment. So for example, we train our graduate students to help you with applications for fellowships, talks at conferences, paper manuscripts, PhD theses, department seminars, even faculty applications. Many of our communication fellows have helped our students become professors or land jobs in industry. And our students have said directly that communication was a huge boost to their ability to innovate in the nuclear sector. Like Adrien Couet just mentioned, communication is equally important as the science. The pitch competitions, these nuclear innovation boot camps, It's about 50% your idea and 50% how you describe. So with that, I'd like to stop. And I'm happy,英語でも日本語でも質問をできるまで答えます。
マイク先生、どうもありがとうございました。
Professor Michel, thank you very much for your presentation.
これから質疑応答に入りたい。
So right now, we'd like to move to the Q&A session.
質問がある方は
Do you have any question? Would you actually utilize the Q&A box to raise a question?
どなたか質問ありますか？
Are there any questions? It might be very difficult to raise a question to you. Okay, I have a question.
Mm-hmm.
You showed us a very good educational activity in the and it seems students have a lot of opportunities by themselves.
Mm-hmm.
So is there any special factory or a workshop for the students?
So is there any special workshop for students? You mean that that MIT offers, for example?
MIT の中で学生が授業で使うためのワークショップがありますか?
Yes, are there any additional workshop in that MIT for the students?
Yeah, so we do hold many smaller workshops for students on selected topics, such as scientific communication, let's say accelerator physics, anything that the students are interested in, we can arrange such workshops. We also hold professional education workshops, and we invite our students to join in. So you can meet with the leaders of nuclear industry, electric utilities, national laboratories, and government research organizations to learn how to obtain funding, to make connections for a job, and to learn which research projects are most important to the industry. Many of our students have gained actually high-paying jobs from participating in these professional workshops, which students get to join for free.
Thank you. And in addition to that, I have another question.
Mm-hmm.
For example, you introduced us the experiment using banana. I think they are very interesting for us.
Mm-hmm.
But, to do such a laboratory class, you may does MIT support such educational activity or?
Yes, MIT supports these educational activities very strongly. So this year, for example, I requested something like $15,000 for educational activities to buy a light board. I should show you a picture of what this looks like. So as you know, it was very difficult this year to teach because of COVID. So I'd like to show you what we set up in order to make more easy access to, I'd say, high quality nuclear education. So for example, I asked the nuclear department to purchase this light board for us. So we could, or I could teach as if I was at the blackboard. This cost $5,000 and our department said, no problem. I asked my department also for $3,000 of reactor usage time for the toenail experiment. No problem. I asked to buy 50 kilograms of wasabi peas and gummy worms to measure gamma activity. No problem. $7,500 for Geiger counter kits. No problem, because we strongly believe that these hands-on experiences are a very small investment. If we can spend a few $1,000s now and we gain one talented student, they could have a huge return on investment for the benefit of nuclear power. So when it comes to investments of hundreds or thousands of dollars for nuclear education, MIT always says yes. I did ask them to buy a Mongolian Gare for additional $6,000, and then they said no. But that's because I already spent so much money on the design course, Geiger counters, toenails, radioactive food. I had my students get X-ray scans to measure their muscle and body fat percentage. I have a really long list of these activities, and they said yes to very many of them. We want to invest in you, is the answer.
Okay, thank you very much.
他に何かご質問はありますでしょうか
Are there any further questions?
Okay, can I ask you something?
Yes, please.
Yeah, you said the communication is very important in engineering, and maybe some students are not good at the communication. How do you encourage communication for those students? Do you have
good question. So to encourage communication for all students, within our classes, we have a communication requirement that some of our classes require oral presentation and written documentation, not just lab report, but we teach video creation, modern media creation. The communication lab is there for any sort of communication exercise the students need. We ask the students to give a seminar twice a year and poster once a year on their research. And it's required to meet with the communication lab multiple times to make the presentations good. And I can say 5 years ago, we did not have this communication lab. Most of our posters were really terrible. It was not fun to watch these presentations. 5 years later, after implementing communication lab, our students' posters, all of them, are much better than a professional conference like American Nuclear Society or Materials Research Society. Our students are much, much better. Because now, when students see everyone around them communicating effectively, they want to meet that same level. So low level is no longer good enough. We have so many people who have become so good at communication. Everybody wants to achieve this high level together. In addition, the department has a fund to send every student to a professional conference at least once per year. So if you want to present your work at a professional conference, we provide you the funding, and we provide you the communication tools to make your presentation excellent.
Thank you. Great.
Sure.
他にご質問はありますか
Do you have any more questions from the floor? Any questions, please?
Is the field of nuclear power popular at MIT?
はい。
So it is.
原子力科学は MIT
どうぞ通訳どうぞください。すいません。So yes, I'd say the field of nuclear power is equally popular at MIT compared to other schools in the US. About 1% of MIT undergraduates study nuclear engineering. However, with the growth in fusion power and nuclear medicine, many students from other departments are taking our courses. For example, this year I taught Introduction to Radiation and Nuclear Engineering. We had 25 students, but only 10 were nuclear engineering majors. Our graduate program is much bigger. We usually have 120 to 150 graduate students, which is more like 3 or 4% of the MIT population. The reason for this is there are very few undergraduate nuclear engineering schools, but you can join nuclear engineering graduate school if you are a mechanical engineer, chemical engineer, political scientist, anthropologist, almost any field, applied math, physics, chemistry, it's all good. So thank you for the question.
他にはまだご質問ありますか？
Any more questions from the floor?
では質問ないようであれば、次はパネル
If there's more question, then we'll jump into the panel discussion. Thank you very much, Professor. It is fabulous. Thank you so much.